already started? Okay, nice. So yeah, I mean, thanks for coming to the fourth tutorial of this quantum error correction tutorials. And yeah, I mean, so as we discussed, so far we have discussed, basics of quantum error correction, classical error correction, and the stabilizer formalism. The second tutorial was about toric code. The third one was about introduction to topology. And today we are going to talk about topological quantum codes, bosonic codes, and subsystem codes. Nice. So this is the overview. So we will recap, as always, what happened last week. Then we will discuss, the notion of topological quantum codes, explain toric codes in the topological language. Then bosonic codes, some codes. So we will see that, how we can do error correction in the continuous variable systems, like a degree of freedom. And then subsystem codes, which are, generalization of stabilizer codes. And finally, I will summarize. So let's start. So to recap, last time we discussed about topology, and we discussed this notion of Euler characteristic. So it can be for surfaces like this, it can be given by vertices minus edges plus faces. And you see that it's all true in these cases. And actually, this Euler characteristic can be written as alternating sum of something called Betty numbers. And Betty numbers, is something which people talk when, often when they are doing data analysis, they are interested in these Betty numbers. And we also discussed that, two now objects, they are topologically equivalent if they are equivalent up to homeomorphism. So basically, a continuous map, both sides, bi-invertible. So if you can go from, let's say, so that's why, when people say that a copy mug and the torus, they are equivalent, topologically equivalent, it means that, you can go from here to here via homeomorphism. Okay. And then, we discussed many things, we talked about, the different Euler characteristic for different objects, and so yeah, and basically it was a topological invariant, and under homeomorphism, basically topological invariant remains unchanged. Then we discussed this notion of cells. So basically an n cell is an n-dimensional object in a cellulation. So cellulation, you can think about, it's basically, let's think that, so you have these soccer balls, right? On that you have hexagons and pentagons, so you can think about that's like a cellulation. You cellulate the surface. Similarly, you can take a torus or any object and you can cellulate it with some polygon. So that's how we generalize that's how we calculate Euler characteristic for the objects which are not polygon. So basically you cellulate with a polygon, and then you can count vertices, edges, faces, and again you can calculate the Euler characteristic. So basically a zero cell is a vertex, one cell is an edge, two cell is placket. So we and then we discuss the notion of zero chain between assignment of element of Z2 to every vertex. So you can think of that, you have a set of vertices, and from that set, you are interested, only in a subset of vertices. So you will assign 1 to them and 0 to others. So one chain is nothing but, a particular, a subset of the set of vertices. Similarly, two chain, you can think about, it's assignment of 0 or 1 to every placket. So again, you can think of it as a subset of the set of plackets. And similarly, we can talk about n chains. Then we discuss the notion of, like the boundary operators, which basically the boundary map, which, like acts on a chain. So it acts on n chain and, and gives us, like an n-1 chain, which is the boundary of the original chain. So for example, here it at the del 2 will act on it, and you see that, like you get the object here. And yeah, you can see. So that's nice. I mean, we have this. Yeah. So yeah, you can see that this will be the boundary. Yeah. So that's what you get here, right? I mean, yeah. Very nice. Then, like, using this operator delta n, you can define Cn, the full group of n chains, Zn, the subgroup of n cycles, and Bn, the subgroup of n boundaries. So basically, Cn is the domain of delta n. Boundaries Bn is basically image of delta n, and Zn is basically the kernel of delta n. So all those, like chains, which are, like, which are not boundaries of all the cycles. So basically, given a cycle, it can be a boundary or it cannot be a boundary. Like, I mean, so, but all boundaries are cycle, but not all cycles are boundaries. So using this idea, I mean, you can use the notion of boundary to define the this object, this quotient group, which is, like, so basically you start with Zn and quotient into Bn, and what you get, that you call the homology group, like nth homology group. And the rank of the nth homology group is what we call it, what is the nth Betty numbers, and it's nothing but rank of Zn minus rank of Bn. Like, what is rank? You can think it's a bit involved, but you can think of, as like dimensionality, like, or something like number of independent components, like, so there is a nice definition in terms of like for abelian groups, at least that's what, like often we will be interested in. So, and then we discuss this fundamental lemma of homology, which says that boundary of boundary is a null chain. So basically, if you look at a boundary, if you have a boundary, and if you try to find the boundary, if you apply the boundary map on a boundary, like n boundary, basically, like you will get a null chain because a boundary does not have a boundary. And then so we discuss all these notions, and then after that, like we also talked about cohomology groups, which are analogously defined using something called n co-boundary maps. So you have the n co-boundary map, and how do you define the n co-boundary map? It is defined through the boundary map. So let's say you have a chain, like so let's say C is a cell and P tilde is a co-cell. So basically, the way, like, so you can think what this might remind you of, like when we have operators A and then U acting on psi, and then you take U on the other side and write like that. So it's similar to that, like it's basically delta n plus will go from here to here, and you get, like delta tilde n. So this is a defining equation for the co-boundary map. So basically, today we will be using this fundamental lemma of homology a bit, and also this defining equation for the co-boundary map. So you can think about, like it's like the dual object for, like corresponding to the boundary. Yeah. So basically, delta n tilde is, let's say, the n co-boundary map. So again, like, it will take you, like it's like the co-chains, they will be the set of co-chains will be its domain, and basically the kernel will be Zn, and that's what we call the co-cycles, and the co-boundaries basically, like the set of co-boundaries, it should be set basically. So that's basically the image. And now again, you take the quotient of the kernel with respect to the image, and you get this group called the nth cohomology group, and you can analogously define the corresponding Betty numbers. So that's what we discussed so far. And now we are going to, use all these ideas for topological quantum codes. Then we will see how we can, go for the continuous systems, and then how to generalize it beyond the stabilizer formalism using subsystem codes. So let's remind ourselves, the toric code. So in the toric code, we had, qubits at these locations. So you see that, these are all qubits, wherever there is a white dot, that's a qubit. And you had these vertices here. So we have these vertices, and these are the plaquettes, this is a plaquette, and these are, edges. So so regular, everybody knows what's a plaquette is, edge, and all those things. So you have L cross L grid periodic boundary condition, and we have this, so these are our plaquettes operator, and these are the vertex operator. So let's look at, all this in the language of homological terms, in a homological language. So the edges are 1 cells, vertices are 0 cells, plaquettes are 2 cells. Dual lattice, that's basically, a set of co-cells. Dual lattice plaquettes, it's basically 0 co-cells. So basically, plaquettes are, 2 cells, but there they become 0 co-cells. And edges, 1 co-cell, and vertices will become 2 co-cell. So you can think about, it's dual in that sense also, So nice. So basically, let's first set the stage. Where we have the qubits, and what are the operators and so on. So qubit basically wherever every 1 cell and every 1 co-cell, intersects. That's what that's where the qubit is. So you can see, right, these dashed ones are the lines, the dual lattice, and the solid ones are the lattice, and wherever they intersect, we have a qubit there. So you see there is a qubit here. Okay. And the tensor product of Pauli Z operator, we we represent that by 1 chain. Tensor product of Pauli X operators, we represent that by 1 co-chains. So a Z chain operator, we will write that, tensor product of Z, power X, where X in C. So let's say X can be 1 or 0. So depending on, let's say, if a set of sites are involved, so Z will act there. If it's not involved, then it will be Z power 0, that will be identity. So it will act trivially on those sites. X, basically a group element, assigned to 1 cell in C. And Z0 is, basically is, that's identity. Yeah. Similarly, you can define a X co-chain operator. Yes, so on. Yeah, analogously. Now, every n qubit Pauli operator can be written as, linear combination of the product of, this X co-chain and Z chain. That's all. This is regular, algebra. Now, if you look at the inner product between X and Z, that will be basically XZ is -1, this inner product modulo 2 ZX, which means XZ equal to 0, they will commute if this is equal to 0. So that is what so basically, even though we started with X and Z, at the end of the day we will be only talking about the plaquettes, basically cells and co-cells. That's what we will be talking about, because they will govern whether the corresponding operators commute or not. Nice. So let's first define what are the stabilizer generators. So stabilizer generators are associated with the boundaries and co-boundaries of 2 cells and 2 co-cells. So basically, you could now you may remind yourself that like the two cells, like they are basically the Z, which were the plaquette operators, and these are nothing but the boundaries. And the two co-cells, for them you get the vertices as the that's they're the co-boundary. Now, so it's associated with vertex generator, which is zero co-cell. Yeah. So basically, plaquette generator, it's associated with a two cell C, and it's defined as a Z chain operator, Z delta C. So basically, Z will act at the boundary. So corresponding to the boundary chain that you have here, you have Z acting on those sides. So and basically, so delta C is also a chain, right? And as we defined before, like you can see, delta C will be another chain, and that will be a boundary chain, and corresponding to that, you can define a Z chain operator. And that is, we are claiming that that's a, that will form a stabilizer. Similarly, for the vertex generator, you can define in terms of X, where, delta tilde is a co-boundary of P tilde. Now, the question is, why? Why it should be a stabilizer? Just because we define it, we need to prove that, all these Z commute among themselves, all these X commute among themselves, and Z and X commute among themselves. Now, all the Z will commute among themselves. That's trivial. All the X will commute among themselves. That's also trivial. But Z and X, whether that will commute or not, that we will see now. So you see that, it's very easy to see that, X and Z commutation. Why that 0? Because X and Z equal to 0, it's nothing but looking whether, is this delta tilde P tilde and delta C, where they're, the inner product modulo 2 is 0 or not. So, but we know that, delta tilde P tilde delta C is nothing but, P tilde delta C by using the definition of co-boundary map. So if you remind yourself, when we define the co-boundary map, you can take your delta from here, to here. Yeah. So that's what we know. We will get delta C equal. Yeah. But we know that from the first fundamental lemma of homology, that boundary of boundary is 0. So delta C is 0. And since we know that, since 0 is a null chain, its inner product with any co-chain is 0. So basically that means, we get here 0. Yeah. So that's the simple proof. So now you see that it's so easy. You can, using this, you have some chain C. So basically you look at, corresponding to the, so the stabilizers, now if you think about it, they are given by, they are the elements of the boundary group. That's how you can set of boundaries. That's how you can think of it. So that's nice. We have a very nice characterization of a stabilizers, because when we need to only look at here we are talking about a particular cellulation, in terms of squared, but you can think about some other cellulation, and whatever we discussed here, the proof here, that will be valid. There is there is nothing about what cellulation we are using here. So that's nice. So next, let's come to logical operators. So what will be the logical operator? So the properties of logical Pauli operators are that they should lie within the centralizer of the code, if you recall from the first tutorial, and that is they commute with every stabilizer. Second, I think I missed something. And they are basically, you can divide them into equivalence classes using the up to multiplication with a stabilizer. So something is missing here, like equivalence classes via multiplication with stabilizers. Yeah, something. Anyway, so So let's first look at, like how do we define the encoded Z operator? So the Z operator, so the Z operator should commute with all the stabilizers, Z stabilizers, all the X stabilizers, and at the same time should not be a Z or X stabilizer. I mean, that's what a encoded Z operator should be. Now, earlier we were looking at it in the group theoretic picture, but now you can look at the same concept using using topological idea. Now, since any Z chain will commute with the plaquette generator, it suffices to find Z chain that commute with the vertex generators and are not one, like, and also cannot be generated by a plaquette generator or vertex generators. So basically, we need to find chains C which commute with X, like vertex generators. So the vertex generators, as we say, like they are given by like basically X co-chains, where like so that's what we define here, right? So corresponding to co-cell P tilde, the co-boundaries of P tilde, like that gives us the vertex generator, and we need to have X delta tilde P tilde, which is basically a vertex generator that should commute with our Z chain ZC. But we know that this is nothing but delta tilde P tilde inner product C equal to 0. So this is equal to 0. This is nothing but like you can, using the definition of co-boundary, you can take your delta here and P tilde delta C equal to 0. And so this is only 0. So P tilde is not 0. So this is 0 only if like delta C is 0. So basically, when is delta C 0? It's basically the set of like chains, one chains basically in our case, with 0 boundary. So what are the set of one chains with 0 boundary? It's basically it's a non-trivial cycle, right? I mean, so that's what so that's the definition of a cycle, right? The set of Z chains which commute with every stabilizer is a set C, like it's basically a cycle, right? Because when you act, we know that cycle is nothing but the kernel of the delta operate, like the boundary map. So in like it can be a trivial one or it can be a non-trivial one, but the trivial ones are since already are also boundaries. I mean, we are not interested in them. We are only interested in the non-trivial ones, so basically the non-trivial cycles. So like that's what we will give which will give us the encoded Z operator. Similarly, encoded X operator, you can play the game like the encoded X operator should commute with all the Z, so Z delta C here, so that the P tilde delta C equal to 0. Now use the the definition of the co-boundary map, so you get something like this here. But like C is not 0, so this should be equal to 0. So P tilde is a one co-cycle. So the logical Z operator are basically one cycles, and logical X operators are one co-cycles. But yeah, like I should also write here, this is the non-trivial ones. Like they should not be the trivial ones, because the trivial ones are stabilizers. I mean like they are boundaries, so they are like also already in the stabilizer. So you see, right? I mean, earlier we saw like in the toric code, like this was the non-trivial cycle Z, X, so basically you corresponding to so the Z ones you get corresponding to cycles, and corresponding to the dual lattice, like you get here the one core cycles you get, like they are the logical X operator. So now everything fits perfectly. Like I mean, what we discussed in the second tutorial, like and the last one, and also the first one. Like I mean, so if you think using all the language that we developed in the last 3 tutorials, I mean, we are able to describe stabilizers. We are able to describe logical operators, and then yeah, so that's nice. Okay, so But to complete the analysis, we must group the logical operators into equivalence classes. And if you recall, like earlier, let's say this is a stable, this is a logical operator, then this is also a logical operator, and this is also a logical operator. And the idea was that if you multiply with a stabilizer, it will still remain a logical operator. So we had equivalence under multiplication by stabilizer elements. And the stabilizer elements are given by one boundaries and one co-boundaries. And so basically what we need is equivalence up to addition with one co-boundaries, one boundary and one co-boundary in our case. So this is nothing but the definition of homological or co-homological equivalence, like in the previous tutorial. So so let's say you have a chain, and if you add a boundary to it, and so basically, so basically up to addition up to boundary is like addition up to boundary is basically a trivial operation. If you think about it in terms of error correction also, like as we discussed in the very first tutorial, that let's say you have some state psi and you act on it by L, like some logical operator, or you act on it by like ls psi, like both will be same, because s psi is psi. So and s is like a boundary, and and if you think about the homology groups are defined as Z and Bn. So basically you factor out like the boundary, like you are not interested in the boundaries. So it's like thinking about for example, if you let's say think about the set of integers modulo 5, then the number 1 and number 11 are both same, because like you can add a multiple of 5, which is 10, and you can go from 1 to 11. So it's like that. Yeah. So very nice. Where like group theory and topology are very nicely coming into play to justify things. Okay. So basically the logical Z operators, they are basically identified at the element of the first homology group, and the X operator, they are the element of the first co-homology group. And these are the corresponding Betty numbers. And the number of encoded qubits, it will be nothing but rank, because now you can do the reverse engineering, and you can think about like we have those many logical operators acting, so how many qubits you should have, and that's what will give you the number of encoded qubits. So that's nice, very nice. So we had everything, but one could ask what about distance? Now you cannot get everything, right? The distance of a code is not determined by homology of the code, and is not a topological property. It depends on the implementation, what kind of lattice you are using, and many other things. So then this is a not so good news, but that's how it is. So the next we need to discuss error correction and detection in the topological language, and that will complete our discussion about topological quantum codes. So let's first when we think about error detection, let's first discuss Z-type errors. So again, any error basically will correspond to certain Z operators acting at few places, and you can represent by some Z chain. Now to detect it, you will measure your stabilizers, which are given by x delta tilde p tilde, corresponding to a co-boundary map acting on some co-cell. And so basically, how will you detect it? Let's say if they commute, then you will not detect it. So the only way you will detect it if if they don't commute. And so if they don't commute, then it means that the inner product, that's equal to 1, because there are only two values, like it's 0 or 1. So it's not 0, so it's 1. Since it's not 0, so it's 1. But we know that this is nothing but p tilde delta is equal to 1 from using the definition of co-boundary map. Yeah. So the set of vertices whose outcomes are flipped by Z error, basically are the 0 co-cells p tilde. Like you look here. which intersect the boundary of C. So you have C, and there will be, you know, like this boundary of C, and all those, you know, like what is zero core cells P tilde, who, like, you know, who intersect the boundary of C. That's what, you know, like will detect the error. So you can think about, you know, like, let's say you have a error something like this, and, you know, like and so here you will be able to detect it using, you know, like the operators, which, you know, like the stabilizers, which correspond to action at the boundary. So that's how you will detect it. So that's nice. And you can similarly talk about, you know, like the X type errors. So they are represented by the X cochains, and the errors are detected by measuring the placate stabilizers. So again, you can do the same analysis, and the syndrome measurement associated with X cochain is the set of is basically the set of placates at the co-boundary of this cochain. So basically, I mean, an error will correspond to a chain or cochain, and you will measure it, like, you know, the operators, which, you know, like so the stabilizers at the boundary of this chain or cochain will detect it. And you can ask the question, you know, like, given a chain or cochain, there can be, I mean, given a boundary, you know, like there can be multiple chains or cochains, you know, like which connect them. So how do we know which error has occurred? And that's the problem. And, like, you know, when we will discuss about decoders, we will try to understand it. So the error correction is the job where, you know, like so let's say you had some error, and we discussed that, let's say if you perform a chain, you know, like some correction operator, such that overall they form a, you know, like some site, you know, like some stabilizer, you know, or you could say boundary, then you will be able to correct it. So basically, ZC prime will correct ZC, C prime equal to C plus B. So now you see that, you know, like how everything is fitting. Like, I mean, earlier, I mean, we were talking, I mean, we had the physical intuition already, but now, you know, like in terms of like, you know, like, you know, chain operators and, like, you know, co-chain operators, you can discuss whether, you know, like, you know, whether you will be able to correct or not. But what if, you know, like C prime is not equal to C plus B for any boundary B, and, you know, like that will lead to some logical error. So, I mean, in how, like, you know, can we avoid the logical error in certain cases, like, and to what extent we can avoid, and all those things. This will be a topic of, you know, like decoders. I mean, so when we will discuss decoders, you know, like in the next tutorial, I mean, we will delve into these things in detail. Okay, so by now, I think many of you might be, you know, like I don't know, like frustrated, fed up, or or sad with too much topology. So it's a time to take a break where, you know, like for a while, I will not talk anything about topology, you know, like and using some basic algebra, we will be able to, you know, like discuss again. So those of you whose camera is, you know, like off because of too much topology, maybe you can, you know, like turn it on because we are going to talk about, you know, like some simple stuff here, like relatively. So we will discuss about, you know, like Bosonic codes and the later subsystem codes. And I think the next two tutorials, I think there will not be much topology also. But you can see at least you should, you know, like you can appreciate that how powerful this topological language is, that, I mean, which can help us generalize the notion of, you know, like starting with toric code, stabilizer code, you can discuss everything, you know, like in terms of boundaries, cycles, homology groups, you know, like cohomology groups, and so on. Yeah. So nice. So basically, let's look at, you know, like the Bosonic codes. So first, let's look at, you know, the classical paradigm. So classically, there is this notion of, you know, like coded modulation scheme. So it's a robust encoding of, you know, like classical information into, you know, like frequency, amplitude, phase. So the people who do classical, you know, like coding and all, like I think electrical engineers, they will tell us about, like they know more about this thing. So you have, you know, like Vt equal to, let's say, It cos omega t plus Qt sin omega t, where omega is, you know, like the frequency of the carrier wave. And you can take this I and Q and you can write it as some complex number Z. So this I is called the in-phase amplitude and Q is called, quadrature phase amplitude. So there are different kind of encodings, like, so there's something like, there's phase shift encoding, like keying, quadrature phase shift keying, this one, and quadrature amplitude modulation, like 16 QM. So this PSK, like you can think about the CAT codes when people talk about, like many of you must have heard about the CAT code, like that's basically generalization of this one. Then the four-legged CAT code is generalization of QPSK. And the GKP codes, like, Gottsman, Hitayev, Preskill code that, like many of you might have heard of, that's a generalization of this one. So you see that these ideas are, classically present. And I think it seems that the bosonic codes are relatively less explored area. And there is, like a lot of room for, progress here. So this is the, the correspondence between classical and quantum keys. So you have the classically, coded modulation scheme, and here you have this boson encoding and so on, you can access the slides later. So GKP codes, it's basically, so you see that it looks like a lattice structure, right? And recently there was a nice paper by, Conrad, Isat, and Arzani, where, they looked at the GKP code and this lattice perspective. Yeah. So let's, look at certain example of bosonic codes. So boson, there, there are two famous examples, which are, like bosonic stabilizer codes and bosonic Fock state codes. Like we will focus, on bosonic stabilizer codes here. So they are the generalization of qubit stabilizer codes. So we are talking about a stabilizer code so far. So we will, like here also we will talk about a stabilizer code. And then finally, like we will deviate a bit, like when we talk about the subsystem codes. So this can be formulated in using position, position states. Yeah, and the examples are, like the examples of these are analog, not analog, sorry, analog stabilizer codes, GKP codes, and GKP stabilizer codes. Similarly, they are like, bosonic Fock state codes, which are, like they stray away from the stabilizer framework, and we will not discuss much about this today. We will not discuss about this today. Can be formulated using Fock states, and the examples are, like SCAT codes, binomial codes, Chebyshev codes, CLY codes, dual rail codes, and so on. And there are many benefits of, using bosonic codes, and you can, like in this nice notes by Victor Albert, you can read about this, and he like mentions there that like they can utilize hardware in a more efficient way, then finite dimensional discrete variable codes can help improve performance of discrete variable code by something called concatenation. We will talk about it later, in the next tutorial. Allow for whatever, basically they are useful in many things. Yeah. So that's nice. So let's look at, first try to understand, like for this bosonic code, people talk about in this notion of bosonic modes. So what are bosonic modes? So basically these are, these are described by continuous conjugate variables, also known as, like quadratures. And so they are continuous variable mode, some people call them Q mode, or more colloquially, like also called like harmonic oscillator, abuse of language, maybe you can say. So examples of, like bosonic modes are electromagnetic mode of a microwave cavity, an optical cavity, fiber, or, like a free space. I think something is missing here again. Yeah. And then you can also have you can also encode into like mechanical modes of vibrating atomic or molecular nuclei, or acoustic, or, nanomechanical resonators. So there are different ways you can different ways you can access, like bosonic modes. So, so basically, like when we talk about bosonic modes, you can describe them via position states or, like Fock states. So position states, you can think of them as a set of, canonical, so these are states which are, like orthogonal, but like not really normalizable. Like, I mean, a mathematician will not be very happy, like, with this Dirac delta function. But, like they are complete. I mean, you can see, like, this I take from the notes by Victor Albert. So, like, they are complete, and, you can define, they provide a basis, like, and you can describe something like a position operator and like momentum states, like, which are, you can think about, like the Fourier transform of the position states. I mean, like, these are like, regular quantum mechanics 101, like many of you might have already know, like, yeah. And we have this Heisenberg, like uncertainty relation. So another, like this notion is this Fock states. So this forms an orthonormal basis for a single mode again, and they are the eigenstates of the occupation number operator. So you can, like use like position operator and momentum operator, and using that you can, like form your NK, like this number operator. And the number operator, when it acts on, like a Fock state, it gives you, like counts how many, let's say, photons are there, like the single mode excitations are there. And the N cap, you can write as a cap dagger A cap, and the A cap is, like I think it should be, yeah, I think maybe there is no square root here. Yeah, I think I messed up here. Yeah. So yeah, I think you can check this one. Okay. So like, when we talk about bosonic codes, we will focus on here on, like bosonic stabilizer codes. And so to define that, like first we need to define this oscillator generalization of X and Z. So there are, like two objects here. The first is this thing called a position shift. So basically you can think of them as, like similar to the X operator. So like when X acts on, for example, in the case of qubits, when X acts on 0, it gives you 0 plus 1. And when it acts on 1, it gives, like 1 plus 1. Like, I mean, that's how you can think of. So when it acts on Y here, position shift, like it gives you Y plus 2. Momentum shifts, like they are diagonal, and they are more like, the Z operator you can think of. So when they act on IQXY, it will just pick the Y, which is present here, like IQY. Here Y is a position state and Q is a real number. And you can show that for momentum states, like the EIQX, it will shift the momentum state, while, like this E minus IQP cap is diagonal. So it's like, the similar to the X and Z basis, like transformation. Like you can work in the computational basis, or you can perform the Hadamard transformation and go in the X basis. Yeah. So basically, the commuting set of displacement operator, they will define our bosonic stabilizer codes. And so earlier, like we were looking at NKD, and the encoding was, like with respect to qubit, you can think about like 2 maybe. Now here you have, real. So you have like, K logical modes, which you encode using N physical modes, and it can detect error, like acting on at most D-1 of the modes. Now, like you can, like this reminds very much, like of what we studied in the stabilizer code. That's why it's like, bosonic stabilizer code. And correct errors acting on at most D-1 by 2, like the floor of that modes. Yeah. So there exist analog versions of, like qubit repetition code, 412 code, Shor's 9 qubit code, 5 qubit code, like the 513 code, surface codes, and many of them. And many of them have not been, like they're like explored. And I think that's where there is, like a good opportunity to explore and all. So let's first look at, maybe we'll just discuss, like how to look for the 412. I mean, we will look at the example of the 412 code. So the 412 code, like is given by, these 3 stabilizers, yeah, and their generators, and this is the stabilizer group, and these are the logical states. So again, in the analogous case, like you can define the stabilizer generators, like as S1 is e to the power I, x1 cap minus x2 cap, S2 is this one, and S3 is this one. You can see it's very similar, right? I mean, S1 is x1 cap minus x2 cap, like which is like, Z acting here, and this is the position at x3, x4, like Z3, Z4, and then you have P1, P2, P3, P4 is like x1, x2, x3, x4. So like there is a bit of similarity, like you can see here and here. So the joint plus one eigenstate of S1, S2, and S3 that will define the code space, and you can like take these objects like downstairs, and so basically let's say if the code space is a plus one eigenstate, then if you act by like whatever is in the exponent, then you will get 0, right? So these are called the nullifiers. So if you act by x1 minus x2 on your x4 mode, you will get like 0 here. Yeah. So that's another way. And measuring x1, x2, like x3, x4, like these are Hermitian operators, and like you can measure them. Like there are nice techniques, I think, in quantum optics and all. These experts in the audience know better. Like you can measure them like effectively. Yeah. So that will use to detect one. So let's say if you get if it's not 0, then you will be able to detect it. Yeah. Nice. So that was like that's how you can and I think you can talk about like more interesting codes like GKP codes and so on. But yeah, I mean we don't have much time, and like let's proceed to discuss like the subsystem codes. So yeah, so for this one, like I took some information from the Brookman's notes, and also like from a Stack Exchange, like because I found that like a Stack Exchange had a very nice explanation. So let's look at the source 9 qubit code in the stabilizer formulation. So we never discussed short 9 qubit code, but let's today discuss it in the stabilizer. So it's a 913 code. What it means that it has 9 stabilizers and 1 logical qubit. Using 9 stabilizers, it imports 1 logical qubit, and the distance is 3. So like these are the it uses 9 physical qubits. It uses 9 physical qubits to encode 1 logical qubit, and the distance is 3. And these are the the 8 stabilizers you have. So you have you remember like we had this relation n equal to m plus k. So n is a number of physical qubit, k is a number of logical qubit. Yeah. So and m is a number of stabilizers. So here we had like n equal to 9, m equal to 8. So k is like 9 minus 8, that is equal to 1. So you have 1. So this is all great, but like you see that you need to measure these stabilizers to encode information, and that's not a great news. I mean, like because these are like these are like weight 3 operators, which is okay, but these are weight 6 operators, and that's not a great news. So yeah, I mean, and these are the logical operators. That's okay, but you see that. Yeah, I mean, so this is bad. So how can we like get around this? And subsystem codes like provide one way to like get around this problem. So the subsystem codes, they are the generalization of the stabilizer codes, and that the stabilizer codes basically so let's say you have some like a few number of physical qubits. You corresponding to that, you have a big Hilbert space, and the stabilizer codes break that Hilbert space into a direct sum, where like you have a code space, and everything else is like the error space, and whenever your state goes to that outside the code space, you bring it back. Yeah. So but the subsystem codes like do not use this composite structure, like this complete subspace C. Basically in their case, the C is a tensor product of A tensor B. So that's why like it's a product of 2 subsystems. So that's what there is this name like subsystem code, like the C is A tensor B, and here A is used to store information, but B like errors on B are ignored, and they constitute gauge degrees of freedom. So the corresponding qubits you can like whatever the corresponding qubits, like you can think about as the gauge qubits. So let's say if you have n number of physical qubits, k number of logical qubits, q number of gauge qubits, and like the distance is d, you denote it as nkqd. Now given like nkd scheme, what is a good q like I'm not aware of, a nice scheme which, explains these things, like systematically. Yeah. So the stabilizer code is, like 913 code here, but in the subsystem code, what you can do is that you can combine all these stabilizers into, like a small number of stabilizers. Like you have like 1, 2, 3, 4. So now you have all weight 6 stabilizers here. So we are trying to change the 913 stabilizer code. So you have, you combine many of these Z, like you get like 2Z and 2X, but all of them are, like weight 6. Earlier we had, like here only these were weight 6, but now all of them are, like weight 6. So now again, if you, let's say, similar to the stabilizer formalism, if you apply the formula n equal to m plus k, n is, like 9 here, m is 4, then k is 5. So somebody will say that, oh, I have, like total of 5 logical qubits. But no, actually, yeah, even though you have 5 logical qubits, you will not be able to detect and correct the errors. So this 5 gets broken into, like 1, 4. So you have 1 logical qubit, and, like 1 qubit is used to store information, and the 4 qubits, like they are basically the gauge degrees of freedom. So the idea is simple, so even though, these are x1, x2, x3, so yeah, so this is a very nice, on the stack exchange, somebody answered that, let's say these are, like weight 6, but you can measure, like x1, x4, x2, x5, x3, x6, and you can multiply them, and you can get x1, x2, x3, x4, x5. Like, you cannot do this in the short code, because x1, x4 will not anti-commute with the, would anti-commute with the stabilizer Z1, Z2. But here, in our case, like, here, we don't care about, like whether, it commutes or, like not commute, because, it will disturb the state, but it will only disturb the gauge degree of freedom, and not the qubit, like where we want to protect the information. So that is the idea, yeah, that you basically, you measure many of these GIs, the gauge operators, and corresponding to, let's say, you get some eigenvalue, like lambda I, and you take product of I, all of that, and that gives you, like the lambda. So lambda I is a product of all the lambda I. Yeah. And similarly, like, so that was, like Bacon-Shor code. There is also this notion of, like 4-qubit Bacon-Shor code, and all. You can look at, like the references that I provided, and like understand these things in detail. So yeah, overall, basically the message is that stabilizer codes are nice, but then sometimes the checks are, can have large locality, and basically the stabilizers, but you can, using some gauge degree of freedom, you can simplify, and that's what, the subsystem code talks about. That's nice, And actually, there are, like, many other nice family of codes, like color codes, subsystem color code, and so on, which I have not discussed here. But you can look at it, like, or maybe in future, if there is, like part 2 or something, I would like to discuss this in detail. So let's summarize, like what we discussed today. So every, like, qubit basically, like corresponds to, like they live at the intersection of one cell and co-cell. Tensor product of poly Z operators, they are represented by 1 chains. Poly X operators, they are represented by 1 co-chains. So this is Z, this is X. This is how X and Z commutation relation is described, and you can write it in terms of the inner product between the, like the chains and quotient operators, or cells and co-cells, you can say. Placate generators, they are associated with a 2-cell C, and they are defined as, like Z chain operator, Z delta C, and the vertex operator, like you can define in terms of the co-cells. And we discuss, why it's a valid stabilizer generator, why it's a valid choice generator, because, like they indeed commute, and that we proved using the definition of co-boundary, and also the first fundamental lemma of homology. Then we discuss, the logical Z operator and X operator. They are, like the non-trivial co-cycles, like one co-cycles and cycles, and these are the ones, and they are, like there is this homological, there is this equivalence, and the equivalence relation is captured by like addition up to a boundary, and and that's what captures the notion of the first homology group and the first cohomology group, and its elements are like the logical Z operator, and the first cohomology group, its element are the logical X operators. And then we discuss the notion of Z-type errors. Basically, like they are detected by measuring the vertex stabilizers. X-type errors are detected by measuring the placket stabilizers. And that also one can discuss, like in the topological language. And then there was like, there was concern that what if, like if not C prime is C plus B, like where B is some boundary, then it will cause a correction failure. And we will discuss, like decoders, like, this problem in detail without using much topology. And then we have, like we discuss the Bosonic codes, where we discuss about, like displacement and shift, which are, like position shift, momentum shifts, like, they are the oscillator generalization of Pauli X and Pauli Z. And then we discussed about this notion of analog stabilizer codes, where you use n physical mode to encode k logical mode, and like you can detect at most d-1 of the modes errors acting on them, and like correct error acting on at most d-1/2 of the modes. And we also mentioned that there exist analog versions of all these nice family of codes, and there we also discussed this 4-mode code and the corresponding like nullifiers. Then finally, we discuss this notion of subsystem code, where subsystem A is used to store information. This is unlike the case of like a regular stabilizer code, where H is equal to C plus C per. But here, like your C is a like A tensor B, and we discuss, like we have this 913 code. You can break that into the 9143 code, and effectively you have like 5 logical qubits, and you can. Am I still audible? Because when one of my AirPods like just fell on.
Yeah, we can still hear you.
Yeah. Okay. So okay, fine. So basically, like you had like 5 qubits, which are like broken down into like 1 logical qubit, and the 4 like gauge qubits we can think of. Yeah. So that completes the discussion for today. So next week we will discuss about approximate quantum error correction, fault tolerance, and decoders. For the fault tolerance, there will be some topology. There will. So yeah, but it's beautiful. It's good to know things about topology. Decoders, there will be not be much topology, and approximate quantum error correction, there will not be topology. And also this will be the 5th one, and after that, I think the 6th one, will be the finale, where like we will like discuss the exciting stuff, like how it's all related to computer science, many-body physics, black holes, and other crazy stuff. So I think that's all. Maybe I think we can stop the recording and we can discuss a bit. Yeah.